Hey everyone, this is Mr. Warwick, and I'm here to help take you through the notes for 4.1 Shear Transformations and Cavaliere's Principle. I'm going to take you through the first part today. So, slide number 2 says connecting rectangles and parallelograms. Is it possible to have a rectangle and a parallelogram with the same area? Discuss this with the people at your table. Hopefully this should be a pretty obvious yes answer on this one, but we'll kind of go into it here in just a second. And as we look at the third slide, it says, find the area of the different figures. What do you notice? The first one is a rectangle. It has a width of 3 and a height of 4, so it would be 12 square units. We look at the next one, the green one, and it's a parallelogram, and sure enough, it has a width of 3, and we're not going with the slant height, we're going with the actual height, and that is also 4. So this would have an area of 12 as well. Then the last one there, the yellow one, it also has a base of 3, and it's very, very slanted, but it has a height of 4. So with that 4, we understand that it's going to end up with the exact same area. So if we were covering these with paint, we would need the exact same amount of paint to cover each one. As we look at number 4, a shear transformation is one where all of the points on one line are held constant and the other points are moved parallel to that line. It's how we know that parallelograms and rectangles can have the same area. So you see there's a diagonal line that's drawn down through the rectangle, and the area that's kind of, you can consider it cut off over there on the left-hand side, is then moved over to the right. And we see that we have a parallelogram constructed from the pieces of the rectangle. Then the next thing we have on there is, what do you notice about the areas of each one of these triangles? Remember, the triangles are 1/2 the base times the height. And I'm sure you can see where this is going. We have the blue triangle, the green triangle, and the yellow triangle. And for every single one of them, it's 1, 2, 3, 4, 5, 6 across the base and a height of 1, 2, 3. So we can see that all the way through. What would be the line that we're using for shearing? Well, if you go ahead and click to the next page, you can see a direct comparison. It's talking about doing those shear transformations, finding that line that we want to use. And one other thing that we can see when we do the shear transformations is if you draw a horizontal line at the same height, those horizontal lines all end up being the same length, which is especially interesting when you compare the right triangle to the very, very obtuse triangle down there on the bottom. It doesn't seem like those horizontal lines should be the same distance, but they are, and that means that we're covering the same area. That's actually where we get to slide number 7, which is the end of day 1. So that's where we're going to stop for now, and you will be able to complete the shearing transformation worksheet. There's only going to be 4 problems on it. It's kind of, make your own shearing, create a triangle, and a couple of different triangles that are going to be the same. Calculate some area. Just take a look at those kind of things. You'll have to kind of do the work on your own. Can't just copy something that somebody else has put down, but make some shearing type transformations where we've moved across this line and we've created something new that's going to have the same area. Good luck, and I'll check back in again with you for the second part of these notes.